I'm David Wallis. I'm going to be giving the next talk on moving on from the chemical analysis to crystallographic analysis. Just to say from the outset, the various types of crystallographic data that we can get in the SEM are particularly diverse. So my main aim here is to give you kind of an overview of the different flavors of types of data that we can get without going into too much detail. And I'm more than happy to talk about the specifics later in the day. So as a bit of an outline, we'll first say a little bit about how we get crystallographic data using the SEM. By crystallographic data, we're talking about saying something about the crystallography of the particular minerals that are present, how we can identify those minerals, but particularly talking about the crystallographic orientation of the crystal lattices, and also internal distortion of the crystals. So that's what we're aiming for. And as we go along, I'll say a bit about how we work with these, particularly the orientation data, how the lattices are oriented, how we can work with misorientation data. So this is how different orientations relate to each other, or how the internal portions of crystals can be deformed. And similar to Eric's talk, I'll finish up by talking about some recent advances, particularly some things I've been working on with high angular resolution EBSD. So I've kept this talk, it's kind of roughly chronological, so you'll see that the figures get more colourful and the references get more recent, broadly speaking, as we go along. As I said, it's not too technical, and I've tried to include a few references, which are some of the ones that I think to as go-to starting points on particular topics. But again, I can provide more specific references if anyone needs them later on. Okay, so to dive in, a lot of what I'm going to be talking about, again, comes back to the backscattered electrons. So these are the ones you fire your incident beam at the sample. The electrons go some depth into the sample. The electrons are negatively charged and the nuclei of the atoms are positively charged. And so as they go, the electrons are going to slingshot around the nuclei of the atoms in the sample. All those blue ones in this example, many of the atoms will be absorbed into the sample and just fizzle out somewhere. And a few lucky ones, the red ones here, are scattered at angles that mean they're released from the sample surface and ejected again so we can detect them. And as Ollie and Eric have mentioned, most of the time we use these backscattered electrons to say something about the atomic numbers. So larger nuclei are going to interact with the electrons more energetically. So heavy elements are going to lead to more backscattered electrons being emitted. So they're going to show up as light in our backscattered electron image. Lighter elements are going to show up as dark in our backscattered electron image. But now we're going to go beyond that and think about how we can say a little more about the crystallography using some of these effects. So you can imagine that the depth that the electrons go into the sample is also going to depend on the angular relationships between the beam and the lattice planes of the crystal. So in this case, the electrons aren't going to get so far into the crystal, but if they hit at a particular angle, the electrons will be what we call channeled along the lattice planes of the crystal, and many of them will make their way further in. And that's going to actually lead to fewer electrons being emitted again at the surface. So now if we set up our operating conditions appropriately, particularly doing things like a shorter working distance, so that as we scan, this incident angle varies more. If we set up those conditions correctly, we can now get some orientation contrast. So rather than just this phase contrast, atomic number contrast, now this whole region is composed of quartz, and the different grayscales are indicating crystallographic domains with different lattice orientations. So this is electron channeling contrast. These are subgrains within the quartz. Another trick we could play is to keep the beam scanning over a very small region and then we're able to collect a selected area electron channeling pattern. So this is a bit like a diffraction pattern, and different planes in here are going to correspond to different lattice planes in the crystal. These are sort of closely related to EBSD patterns, which we're going to spend most of this talk focusing on. So another trick that we can play is to change the angle of the specimen surface. So most of what we've talked about today so far has been with a flat sample. So that might give us an image like this top one. But you can imagine that if we tilt the sample to progressively steeper angles, more of those backscattered electrons are actually going to make it back out of the sample surface. So once we tilt the sample enough, it seems more appropriate to actually call these the forescattered electrons. And so increasing the tilt is going to change the signal that we get back, and typically it's going to increase the orientation contrast. So here we're now at 70 degrees tilt, and you can see some extra contrast appearing within these grains. This is tilting a bit further, and you can see different features popping up in these images. So again, we can produce one of these forescattered electron images by scanning over an area, or again, we can leave the beam pointing in one place and collect. That ends up giving us a diffraction pattern from that particular location. So that brings us on to electron backscatter diffraction, or EBSD, which is what we're going to focus on mostly in this talk. So typically, to collect these data, we have the sample tilted at 70 degrees. The incident electrons are going in, and they'll actually channel back out along the lattice planes that meet the Bragg condition, and project onto a phosphor screen, which we use as a detector. We image the back of this screen with a CCD camera, and the electrons that are channeled along the lattice planes give us these bands in the diffraction pattern. So the way this works is, this is a great image that I often go to in these kind of talks. This is actually the world record for the world's largest ball and stick model of a crystal structure. This is the salt structure somewhere in Vienna. It's 3 meters across and about 40,000 balls and sticks. And you can imagine that if there were electrons being emitted out of this crystal, coming from the center of this ball and stick model, we're going to receive more of the electrons that are being channeled out along these particular lattice planes that basically we're looking directly along. So these are going to give us the bands in that diffraction pattern. And here's one of these forescatter images, so different grayscales are different crystal orientations. And if we then go and point the beam in different places, we're going to get diffraction patterns where the positions and the orientations of the bands vary depending on the orientation of the crystal, shown by these little cubes. And likewise, if we had a polyphase rock, the diffraction patterns from different crystals would look very different, and again, in detail would reflect the orientation of the crystal. So this is a really powerful tool. We can go and raster across the sample, collect a grid of diffraction patterns, and then index them for the type of crystal, in our case usually the mineral, and the orientation of that mineral at each point. Originally, the solutions to those diffraction patterns all had to be worked out by hand, but now we have very fast image processing techniques to index each diffraction pattern, because we can be working with data sets that these days are up to tens of millions of points. So the way that this works is we take the diffraction pattern from a particular point and use an image processing trick called the Huff transform, which turns all the bands in this pattern, which are quite difficult for a computer to recognize, into a point or a trough, a peak or a trough in Huff space. The peaks are much easier for a computer to pick out, so here they've been identified. And then these can be matched up to a database of crystal structures to identify the bands and index which lattice planes of the crystal those peaks are corresponding to. So now we can say this particular band corresponds to a particular lattice plane in the crystal structure. In practice, the way we do this is going to depend on particular processing software, and I'm not going to say too much about them other than to say that each manufacturer of EBSD systems has its own proprietary software. These days, these are very good and generally make it quite straightforward to perform very advanced procedures. But we now also have a great diversity of freeware packages available for a whole range of tasks. So these are generally a bit more transparent, more flexible, and they're better for development and collaboration. So a couple that I often use, and one of the main ones that's used in the community, is MTEX, largely developed by Ralph Helscher, which is great for handling all the orientation data and all the crystallography. There's other packages. This one, the TISA toolbox, developed by the guys at the University of Maine, is good for thermoelastic analysis. So you can start to go from just the basic orientation data to some sort of physical properties and processes. These two are both in MATLAB, but there's a whole range available in Python and other languages and so on. So how do we actually record these orientation data? Well, in practice, we write them down as 3 Euler angles. And what we do is we have some reference orientation of the crystal. And then these 3 angles are rotations that can take us from that reference orientation. We rotate around the z-axis, the x-axis, and the z-axis again. And by rotating through different angles, we can get from the reference orientation to any measured orientation at any point in the microstructure. So our data set is basically a list of these 3 Euler angles. To visualize the data, one first step would be simply to give each Euler angle an RGB value, and then we can put some colors on the map and map out the microstructure. So this is good because subtle changes in orientation give us quite a large change in color, but it's bad because it's really difficult to actually intuit what the crystal orientation is. You'd have to unwind these 3 rotations in your head to visualize how the crystal is actually oriented at each point in the microstructure. And just a note that all the plots in this section of the talk, the EBSD data, they're actually all from the same sample. So this gives you a flavor for the diverse ways that we can interrogate these data. So for many geologists, an easy way to visualize orientations is actually to plot the crystal axes on a stereographic projection. So here we've got a reference frame defined by the axes of the sample, X, Y, and Z. Maybe the orientations that we measure are random, and then they're going to be scattered all across this hemispherical space. Or maybe in this particular deformed sample, the crystals, the olivine crystals, are actually aligned. So we can see that the 1, 0, 0 axes are aligned with the X direction of the map, for example. So this is an example of a crystallographic preferred orientation with a non-random distribution of crystal orientations. This works all right. This is actually a small subset of the full data, but you can imagine this gets confusing to visualize if you have a huge data set. So the way you often see it is by contouring the density of points in these plots. So if the crystals are randomly oriented, the density is going to be, normalized density is going to be close to 1 all over this space. If they're non-randomly oriented, there's going to be higher data densities, and you usually see this as multiples of uniform distribution. So here there's about 20 times more A-axes than if that same number of crystals were randomly distributed. So you can quickly visualize the preferred orientations of the different crystal axes. But now we can visualize the orientations, but it's hard to relate them back to the map. So that's the direction we're going to go next. So what we've just done for those pole figures is we've basically plotted the crystal axes in a reference frame defined by the axes of the sample itself. But another trick we can do is do the converse and plot what we would call inverse pole figures. And now we're plotting the axes of the map in a reference frame defined by the axes of the crystal. So up here we were saying that the 1, 0, 0 direction up here lies between x and y. Here we're saying that the x direction lies between 0, 1, 0 and 1, 0, 0. So it's the same data but plotted in the converse reference frames. Now we could colour this space, and this is just for a single crystal, so we could plot a map that's coloured by this inverse pole figure for the x direction, and this kind of aqua blue colour is going to show us something about the orientation of the crystal at that point. We can do this for a whole bunch of crystals, of course, and now you can see this is coloured for the x-axis of the map. So all the blue crystals have their 1, 0, 0 direction aligned with the x-axis of the map. These wonky red and pink ones have something more like their 0, 0, 1 direction lined up with the x-axis of the map. So now it's a bit easier to see or intuit how the crystals are actually oriented at each point in the map. Okay, so that's very briefly orientation data, but now we can think about misorientations between the difference in orientation between 2 points in the microstructure. So we typically describe these misorientations as an axis-angle pair. So there's going to be, as you go from one point in the microstructure to the next one, it's going to be, the lattice is going to be rotated around a particular axis by a particular angle. And we can think about misorientations that are intergranular, so between different grains, or intragranular, and how the lattice is distorted within a particular grain. And just to note that with these misorientations, there's actually many possible axis-angle pairs that can get you from one orientation to the next. And the convention is to use the one that has the lowest misorientation angle. So when we think about these misorientations between different grains, just to give an example of one way that they can be useful, if we have a rock where the crystals are randomly oriented, that's to say there's no CPO, then there's going to be some distribution of misorientation angles between all those grains. And on this plot, this is the frequency of misorientation angles. And this black curve is what that distribution would look like if the grains are all randomly oriented. But the real measured orientation might deviate, measured distribution might deviate from that. And this is actually going to tell us something about how well aligned the crystals are. So whether it's a weak CPO or a strong CPO. So if it's a weak CPO, then the measured misorientation angles are going to be close to this distribution that we expect for randomly oriented crystals. But if the crystal axes are really well aligned, then the misorientation angles are going to be, on average, are going to be smaller. So now this distribution is skewed over to the smaller misorientation angles. And we can actually come up with a metric that quantifies this deviation from the random distribution. That can give us a number that can quantify the strength of the CPO, for example. And this is just looking at how well aligned the grains are with one another. Now to say something about the intragranular misorientation. This is that same map of olivine again, but now it's color coded by the angular difference between the adjacent points. So all of these red lines are more than 10 degrees different, and they're the grain boundaries. All these more greenish lines are a few degrees different from their neighbours. And so these are actually like these subgrain boundaries where we have dislocations stacked up into planar features with curvature of the crystal lattice between one side and the other. So this is giving us a great deal of detail about the intracrystalline distortion caused by the defects. We can actually go and analyse that in more detail. So again, we could plot this is the misorientation angles, but I said there's the axes that go with them. So we can plot the misorientation axes in a pole figure. And that, for example, in this case is showing us that the misorientation axes, the crystals are rotated around axes that are going more or less directly in and out of the map. And we can also plot those misorientation axes in crystal space, making a misorientation inverse pole figure. And then we can see that the misorientation axes are aligned with the B axis and the C axis of the olivine crystals. And that actually tells us something about the particular dislocation types that are in the crystal. So these ones, the crystal is bent around the C axis, and that would be consistent with subgrain boundaries formed by a particular type of dislocation on a particular slip system. So we don't need to go into how we interpret that too much at this point, but just to say you can get this really detailed information on the lattice distortion. And then for the last few minutes, I want to build on that and just say something about this very recent work, something I've been involved in, a sort of extension of the EBSD technique called high angular resolution EBSD. A lot of this work was developed originally by Angus Wilkinson and his co-workers at the University of Oxford. This is one of their key original papers. Recently, I've been doing some work applying it to geological minerals, and we've got a couple of papers on that. And it basically, this is a way of reanalyzing the diffraction patterns to get much more precise measurements of the misorientation, which give us better characterization of the dislocation content. But also, really importantly, we can map elastic strain and residual stress that's currently trapped within the crystals. So much the same as X-ray diffraction, for example, which many people might be familiar with, the electron diffraction patterns can actually be themselves be distorted if the crystal structure is under some elastic strain. So if it's the 1,1 component of strain is going to horizontally stretch the whole diffraction pattern. But these distortions are really small, so we need a really sensitive image processing in order to detect them. And similarly, the misorientations, the curvature of the crystal, are going to make the whole diffraction pattern rotate. So these rotations tell us about the dislocation densities, and these elastic strains can be used to simply calculate the residual stresses that are currently trapped in the crystal. The way that we actually analyze these, we have to measure these really small distortions, and we divide the diffraction patterns up into small regions of interest, and then use cross-correlation procedures to map how those regions of interest are shifted in one diffraction pattern relative to some other reference diffraction pattern. So we can map out all these shifts and map how the diffraction pattern itself is actually squashed or stretched or rotated. And the components of that distortion are going to give us the elastic strains and the rotations. So one of the key advantages is that it can measure misorientations, the distortion of the crystal, much more precisely than ordinary EBSD. So here's a nano indent in an olivine crystal, and this plot is the point-to-point misorientations between pixels along this top line in the undeformed crystal away from the indent. So this is basically showing us the noise in the measurement. And for normal EBSD, it's on the order of 0.1 degrees. And for the HR processing, is dropped by about an order of magnitude. And if we take a profile across the indent itself, you can see that with this lower noise, you can resolve the shape of the lattice curvature, the deformation around the indent much more precisely. Because we can measure that curvature more precisely, we can actually back out information on the types and the densities of the dislocations that are causing that curvature in a lot more detail. So this is an experimentally deformed olivine aggregate. The black lines are the grain boundaries, and then the colours here are showing the densities of different types of dislocation. So this is a huge new wealth of detail which you couldn't resolve using normal conventional EBSD. And the last thing to say is that by mapping how the diffraction patterns are squashed or stretched or sheared, we can map the elastic strains and then use Hooke's law to convert those to the stresses. So now this is one map for each of the in-plane components of the stress tensor. And this olivine was actually deformed at about 250 MPa, sort of macroscopic average stress. But you can see that within the individual grains, the stresses are varying by about an order of magnitude more than that. Stresses vary by about a gigapascal over a few microns. And this is really the only way to measure stresses that are currently trapped within the crystals in the scanning electron microscope. So that's about all I wanted to say. Hopefully that's given you a flavour of some of the things that we can do with crystallographic analysis in the SEM, and happy to chat about it all in more detail as the day goes on.